I didn't hear you.
I said, if it doesn't work now, maybe we'll figure it
This
out in
call
the
is
next
now
class.
being recorded.
Okay. Okay. All right. All right. All right. So as I was saying, the SI unit for frequency is hertz. The SI unit, the SI unit for frequency is hertz. Hertz is Hertz. Many a times it's been abbreviated as the H, capital letter H and small letter Z. So just like that. So take note that the SI unit for frequency is hertz. So we've talked about period, we've talked about amplitude, we've talked about period, and now we've talked about frequency. Now, the next thing I want us to look at, because these terms are very important, because by the time they give you problem and they say, find this, find that, calculate this and that, you shouldn't have a problem with that. And that is why I'm taking time to explain these quantities one after one. Now, the fourth one, the fourth term, or the fourth thing I want you to know on this particular topic is angular speed. Angular speed. Angular speed. So it can be used interchangeably, angular speed, angular velocity. Many a time you see them. So they are basically talking about the same thing. Of course, you know that the magnitude of velocity is speed. So the difference between speed and velocity is just their direction. So speed we don't consider direction when we're talking about speed. But in velocity, we consider the direction of the body. Do you understand that? So the magnitude of velocity is speed. So whether you hear angular speed or angular velocity, they are practically saying the same thing. So what exactly is angular speed? Angular speed is simply defined as the angle turned through divided by the elapsed time. The angle turned through divided by the elapsed time. So I can say this is the angle turned through, divided by the elapsed time. The angle turned through divided by the elapsed time. And that is what angular speed is all about. So whenever you hear angular speed, this is practically what it means. And from what I said now, you can deduce the formula for angular speed. This angular speed has a symbol. The symbol for angular speed is omega. So anytime you see this symbol that looks like W, omega. So that is how to write angular speed. So from what we have here, what then is the formula, or how can we calculate angular speed? So it means that this angular speed, from what I said, we say it is the angle turned through. So it is theta, which is our angle, divided by time. So it's just the ratio of the angle to time. That's all. Remember that velocity or speed can be defined in terms of distance and time. So if velocity is distance over time, just as I believe you already know, and I think I mentioned that in the last class, angular speed itself is going to be angular distance divided by the time taken. Do you understand that? And that is exactly what it is. But sometimes we are already used to the fact that this theta is always in degrees. Mathematics, of course, many a time the things we do anytime we hear angle, the idea we have about angle is that it has to be always in degrees. But it is not so for this angular velocity or this angular speed. The angle here is always in radians, because the unit for this angular velocity or angular speed, the unit is always in radians per second. So the challenge is that I have to then know how to convert theta to radians. So how do I do that? This formula can be written in radians as 2 pi all over t. So it means that the right way to actually express angular velocity is that angular velocity, omega, is actually 2 pi all over t. 2 pi over t. Do you understand that? So 2 pi over t, and that is what angular velocity is. And then somebody will ask, where is 2 pi coming from? Now take note that in radians, 180 degrees is actually equals to pi. 180 degrees is equals to pi. And then if I consider one complete oscillation, that is one cycle. So it's just like taking a total angle about a point. So it means that if 180 degrees is pi, then 360 degrees is going to be equal to 2 pi. And that is total cycle. Remember, we are talking about the angular speed being the angle turned through divided by the elapsed time. That is why you have this total distance, which is the angular distance turned through divided by the time. So the 2 pi, please, is not necessarily, the idea here is not that we are just bringing in 22/7. Okay, so it is just conversion from degrees to radians, and that is what it is. All right. And many a times you can even solve your problems and leave your answer in terms of pi. You don't need to put in the value for pi, and you can just leave it like that, unless you're being asked to express otherwise. So that is that. Okay. Now, it means that, but I want us to also know that this theta, or this, just like I wrote here, remember I initially wrote that theta, angular velocity, angular speed is equal to theta over t, where theta is the angular distance, and also we can express this as 2 pi over t. All right, but sometimes the theta can be expressed, theta can sometimes be expressed, theta can also be expressed as s over r. That is it. So this is more like the displacement of the body along the trajectory divided by where the body is, the position down to the center of the circular path. So the center of the mean position. So if I try to use something like a circular object to explain what I'm saying, so of course you know that if this is the center of this circle, every point around from the center to anywhere is actually equal to the radius. Do you understand that? So this S here is just about distance. Of course, this R also is a distance, but the distance in this case, the R is just the distance from where the particle is down to the center of that circular path. So there are many times the question, or you might be given theta in terms of S over R, or you won't even be given. They'll just give you the distance and then they'll put in the radius of whatsoever thing there, or even the amplitude. Because the rate R also, as we proceed, you will see the cases where the R can be likened to your amplitude. So it means also that this theta, this omega, can equally be written as omega equals S all over RT. S all over RT. And that is it. And of course, I'm trying to prove something here. That's why I'm doing this. I'm just trying to prove something here. And you see this thing most of the time in circular motion. Remember I said there's a relationship between circular motion and simple harmonic motion. I'm just trying to prove it so that at any point you stumble upon anything like this, you just know the relationship to use. So this S here is my distance or displacement, and then the T here is the time. And then I can consider this. If I try to separate the S and T, I can write this here as 1 over R multiplying S over T. And of course, you know that S over T is our V. So it means that this thing can be written as V all over R. You see that? So I can write this equation here as V all over R. This is my V. Please, let me write it more properly. V divided by R. You see? So from here, I can now clearly carve out the equation I want us to know, which is the relationship between the linear speed V and the angular speed omega. V equals omega R. It's very, very important. Even though we'll explain this better as we proceed with some calculations. All right, so this equation most likely is most likely to be used under circular motion, because the velocity of a body undergoing simple harmonic motion has other take cognizance with the amplitude and also the position of the body from the mean position. So I will show you the real equation or the real expression to use whenever you're being asked to find the angular speed, the linear speed of a body undergoing simple harmonic motion. And I'll also show you the time where the equation is going to be reduced to this V equals omega R. You see that as we proceed. All right. So the next thing we'll learn or we'll look at is the linear speed. Linear speed. Linear speed. So what is linear speed? Of course, when we talk about linear speed, you already know what linear speed is. You have to consider that this is just, I'll put it this way, just like the instantaneous speed of the oscillating particle as it moves to and fro from the equilibrium position. So that instantaneous speed of that very particle that is undergoing simple harmonic motion as it's moving to and fro, to and fro, to and fro, the speed with which it moves at every instant is called linear speed. At every instant in time, the speed varies. It's not the same. So let me go back to this diagram. The speed, if this body is oscillating, the way it's moving to and fro, the speed here is different from the speed here, is different from the speed here, is different from the speed here. The speed here, it increases until it gets to this point. As it's going up, the speed is dropping. Then when it gets here, as it's falling down, the speed increases. As it gets to the mean position, the speed becomes maximum. Then as it's going up again, the speed is going to be reducing. It gets here, it becomes zero, it falls back again, just like that. So the speed is different at every instant in time. So that instantaneous speed of the oscillating particle as the object moves to and fro is what we call linear speed in simple harmonic motion. And this linear speed can be calculated. We can actually calculate it. So we can calculate it. The linear speed can be calculated. How? By using this formula, V equals omega
Hello.
square root.
Your screen is not showing again.
Really? Okay. Please, is there anyone not seeing my screen? Let me know whether it's general. Can anyone see my screen? Or is everyone seeing my screen apart from the young man that just said something now? No one is responding. Okay. Let me try to check.
So I cannot
Please, you
see.
people, you can see. Okay. It took you so long to talk. It means you are not actually paying attention to what we're doing. Please, as much as you can, just try and pay attention. Okay. Thank you so much, that young man. But you can see the screen now, right?
Yes, sir.
Yes, sir, you can see it
Okay.
now.
Yes, yes.
Okay. So we are still talking about linear speed. Linear speed. And we say that linear speed is simply the instantaneous speed of the oscillating particle as the body moves to and fro from the mean position, as the body is moving to and fro, to and fro, to and fro. And I was trying to explain something using this diagram here. And I said, the way this diagram is, as the object is oscillating, the speed varies from point to point. So the speed here is different from the speed here, is different from the speed here, different from the speed here. In fact, at this point, the speed is zero, which is why the object stops and then falls back again. At this point, the speed is maximum. At this point, the speed is also zero. So you see, as the body is going up, the speed is reducing. As it's falling down, it increases, gets to this point, it becomes maximum. It goes here again, it reduces, it comes to zero, just like that. So if I ask you to find the linear speed, I'm asking you the instantaneous speed at that very position. So anytime you are being asked to find linear speed, they will tell you the position they want you to find it. And it's very, very important. So you'll be asked to find it with respect to the position that will be given to you in that particular problem. All right. So that is what it is. And this linear speed can be calculated by a formula. We can find it using the formula that V is equals to omega. V is equals to omega square root of a square minus x square. That's what it is. So the linear speed of a body undergoing simple harmonic motion. I'm getting a feedback. Please mute yourself. Who is the person? Okay. So the linear speed of a body undergoing, please, I can get a feedback. Can you please mute your mics, please? Only unmute yourself when you want to say something. You have a question, or you just that's the only time you unmute yourself, then you speak. Then I'll hear you. You put it back. Okay. Now I said linear speed. The formula to calculate this linear speed is omega V equals omega square root of a square minus s square, where a, of course, is the amplitude, and the x is the displacement at that point, that given position. The displacement at the given position. Let me just write this as displacement. So displacement, I mean, remember A is also displacement, but A is maximum displacement. So, but X is displacement at the point you'll be given to find the problem. So you always ask to find V with respect to a point, a position on that trajectory. So it's very important. So this is it. So if the, for maximum, remember from this diagram, if you followed what I said now, I told you that at the center, which is here, at the center here, that this simple harmonic motion has the maximum what? Linear velocity. So the linear velocity is maximum at this point. So as the object is oscillating to and fro, the linear velocity is actually maximum at this very point here. And remember, the distance or the displacement of the object from this mean position as it is here is assumed that the body has not moved. So we can say that at this point that our x is 0. So x is actually 0 at this point. At this point here, at the mean position, x is 0. So if I consider just like if you might be asked to find, sometimes the question you might be asked to find something like maximum speed of the body, maximum speed of the object undergoing that motion. So the maximum speed occurs where x is 0, which is the mean position. So for maximum speed, x is equal to 0. And if x equal to 0, I put it back in this formula, I'll be having that v is equals to omega square roots of a square minus 0 square. 0 square is 0. And of course, a square minus 0 is a square. And clearly, so I can write this as just square root of what? Okay, let me do that in the next line. So I can just write this clearly as omega root a square. And then you can see that square can cancel out the square root here. Then I'll have that v is equals to omega a. Now you can now see that this is how to find maximum linear speed or linear velocity of a body undergoing simple harmonic motion, which is also the same as the speed of a body undergoing circular motion. So the speed of a body undergoing circular motion is given as v equals omega r. This one is omega a. The only difference is that in this case, r is equals to a. And that was what I was trying to do in this other slide. Look at this one I did here. I did that v is equals omega r. And here we have that v is equals to omega a. So the difference is just the a and r. They are both talking about the same thing. Okay. All right, so that is that for the linear speed. Now, the next thing we'll have to do is the linear acceleration. Linear acceleration. Linear acceleration. So what is linear acceleration? We are just talking about the rate of change of linear velocity. Of course, you already know that acceleration is change in velocity all over what? Time taking. So anytime you hear acceleration, don't forget that it's just change in velocity divided by the time taking, and that is it. I don't want us to prove formulas because you might not be asked to prove these formulas. You just be asked questions that has to do with just use them and solve it. And that's why I'm just giving you the formulas 1, 1, 1, 1. So nothing so difficult. You can master these formulas. They are very, very easy to do. So I said that linear acceleration is the rate of change of linear velocity. So this is the rates. This is the rates, the rate of change of linear velocity. This is the rate of change of linear velocity. That's what it is. So the rate of change of linear velocity is called linear acceleration. And how do we calculate it? And take note of this, that the linear acceleration is always directed towards the mean position. Don't forget that. And I explained that earlier when I began this class. The same way the restoring force is always opposite, is always acting opposites to the mean position. It's always directed towards the mean position. That is how the linear acceleration also is directed towards the mean position. Meaning, as the displacement is increasing on the other direction, the acceleration is increasing on the opposite direction. Do you understand that? And that is how it is. So we said that the linear acceleration, once again, is the rate of change of linear velocity. And how do we calculate linear acceleration? It can be calculated with this formula that A is equals to minus omega square x. Minus omega square x. That is exactly what it is. Minus omega square x. This minus only suggests that the linear acceleration is directed towards the mean point, the mean position. That's what it means. So as the displacement is increasing this way, this guy is moving this way. Of course, the restoring force is always pulling in opposite direction as the displacement increases. And that is just the reason for the negative sign. So many a times, once you state the formula, you can actually do your calculation without even putting the formula into the negative sign into consideration. But always have it in mind that this negative sign here talks about direction. It only talks about direction. It doesn't necessarily mean that acceleration is negative. And that is it. So this is the formula we can use to calculate linear acceleration. Where this omega, of course, is angular velocity. So this is angular velocity, and the x is the displacement at that very position. All right. So for maximum linear acceleration, let me just write ACC. For maximum linear acceleration, so we have that our x, of course, is equals to what? The amplitude. So anytime you hear maximum, so the displacement there is going to be the maximum displacement. So we can write the equation as that A is equals to minus omega square A. So this is it. But if it is not the maximum linear acceleration you are looking for, you'll be given the position, the distance of the object from where it is to the mean position. It will always be given. It will always be given. So if it's not given, there's no way you can solve the problem. X must be known. Then for the minimum, of course, if X is 0, the acceleration is 0. What that means is that, now let me go back to this diagram. Very important. Let me see, use this diagram here. Or let me use this one. I've been using the other. Now look at this. The acceleration of a body undergoing simple harmonic motion is maximum at this point. It is minimum at this mean position. Take note of that. But the velocity of a body undergoing simple harmonic motion is maximum at the central position. It is minimum at the end. The end I mean is this point and as well this point. Both. So take note of that. That for the velocity is maximum at the mean position. At the extreme, which is the point of maximum displacement, the velocity there is 0. But for the acceleration is maximum at the extreme. But at the mean position, the acceleration is 0. So sometimes you can be asked to find the acceleration at the mean position. Once you hear mean position, the acceleration at the mean position is nothing but 0. So if you are talking about mean position, x is equal to 0. And if x is 0, our a is also going to be 0. Because by the time you put 0 here, 0 multiply anything is going to give us 0. And that is what it is. All right. So what other thing have I not talked about? Okay, let's talk about angular acceleration. Angular acceleration. That's the next one. I might be too fast the way I speak, so that is why later on the video will always be uploaded, so you can always go back and rewatch the video for the things you might miss even as I speak. You understand? Who is talking, please? Can you mute yourself? Angular acceleration. Okay, so this angular acceleration, what is angular acceleration? It's just, we can define, remember, acceleration is always rate of change of velocity. rate of change of velocity. In linear acceleration, we say it's the rate of change of linear velocity. Angular acceleration is the rate of change of angular velocity. That is what it is. The rate of change of angular velocity is called angular acceleration. I wouldn't want to give us a meaning. Okay, let me try to see if I can work out something here. Now, remember, I said that angular acceleration is the rate of change of angular acceleration. And the symbol for angular acceleration is alpha. Alpha. Alpha is giving us rate of change, which is omega over t. But because of the fact that I want to prove something here, I can say, let me write it first. Omega all over time. The angular acceleration is simply omega over time. This omega here is actually the final minus the initial. Of course, what was the rate of change? Final minus initial. You understand that? Okay. But you know, I already told you that omega is equals to what? V all over R. Remember the formula when I proved that V is equals to omega R. I showed you that, or V all over A. So let me use A since we're talking about amplitude. Let me just stick to A. You understand that? So this omega can be V all over A, where A is nothing but your amplitude. Don't forget that. So if I can write this as V all over A, it means that I can substitute V all over A into this equation. I have that alpha, which is my angular acceleration, can be written as V all over what? AT. Do you understand that? Now, if I can write this thing here also as 1 all over A multiplied by what? V all over T. And of course, you know that V all over T is nothing but your what? Acceleration. Change in acceleration. Acceleration is simply V all over T. So if I replace V all over T with A, I have that alpha is equals to acceleration all over the amplitude. Do you understand that? The amplitude, when we talk about this A, remember, I'm using A here, meaning that the displacement is maximum. But not every time the displacement, you can actually be asked to find displacement. I think I have to, for more clarity's sake, let me stick to just using S, please. So I don't assume that the angular acceleration is always at the point of maximum displacement. So I think that's the wrong thing I did. So let me keep to X. So this is omega is V all over X, where X is the displacement from the mean position at any point at all. So from here, if I make the substitution, alpha becomes my V all over xt. And then, of course, which is can be written as 1 all over x multiplied by vt. And v all over t is actually my acceleration a. So I have that alpha is written as a all over x. So you see that. So this is the formula to calculate alpha. So anytime you're asked to find angular acceleration, the angular acceleration is simply the linear acceleration divided by the displacement at that position, at that very position they are giving to you. So if they say the displacement is at the maximum position, x is going to be equal to the amplitude. If it is at a point 4 cm from the mean position, 10 cm from the mean position, 20 cm, you simply substitute and divide it by, you simply substitute there and divide the acceleration by that value. That gives us the angular acceleration. And clearly, if I make a subject, the linear acceleration can also be found by multiplying the angular acceleration by the displacement of the body from the mean position. So these two formula is the relationship between the angular acceleration and the linear acceleration. And it's very, very important. Okay, so I think I've done justice to explaining some of these terminologies. I would really want us to get the formulas first before we start solving problems. But I think we should just take one problem, then we look at the formula for the period and the frequency of a simple harmonic motion. So let's try to see with the formulas we've already listed out. Let's try to see how we can use them to solve problems. And what I will do is that I'll be giving a question that comprises of all, in fact, I'll just give you one question and the question will be just chained, a typical WIEC problem that we'll be using to explain, to relate all these formulas to see how it works when we are dealing with calculation. Now, take down the equation down. I don't have it, so I'll just dictate it out and perhaps write it as the case may be. Now, the question says, so this is our example. The example is that a ball vibrates in simple harmonic motion. A ball vibrates in simple harmonic motion. So you say a ball vibrates in SHM. So anytime you see SHM, we're talking about simple harmonic motion with a frequency of 50 Hz. So the ball vibrates with a frequency of 50 Hz and an amplitude of 4 cm and an amplitude of 4 cm. Now, the question says, find. There are chains of things they listed for us to find. So we are looking for find. They said, find. The first one, they said we should find the period of oscillation. So the period of oscillation, the next one, we should find the velocities at the middle and at the end of the path of oscillation. That's interesting. The velocities at the middle, and at the end, of the path of oscillation. The velocities at the middle and at the end of the path of oscillation. Now, the third one says we should find the acceleration at the middle and at the end of the path of oscillation. So let's write that one too. The third one, the acceleration. Let me write ACC, acceleration at the end, the acceleration at the end and at the middle of the path of oscillation. At the end and center of the path of oscillation. And now the fourth one says we should find the velocities and acceleration at a distance 2 cm from the center of oscillation. Wow, these questions are quite interesting. The velocities and acceleration, the velocity and acceleration at a distance 2 cm from the center of oscillation. And the last but not the least says we should find the angular acceleration at the end of the path of oscillation. So the angular acceleration at the end of the path of oscillation. And these are the questions. And this is more like, this is a typical WAEC question. So if WAEC wants to ask question, or even NECO wants to ask question on this topic, so you may likely expect to see something like this. Of course, you can see that the question they ask is just very simple, but we have many things to compute. They just said a ball vibrates in simple harmonic motion with a frequency, and they gave us the amplitude, and they just asked us to find 5 stops. Now let's try to work it out. Solution. Now, the first question says we should find the period of oscillation. Before you solve any physics problem, I always tell students, list out all your parameters. So you have to list out your parameters before you start solving, as the parameters listed will help you to know what to do. So we're given that the first thing given there is the frequency, and they said the frequency is 50 hertz. So F equals 50 hertz. And then they also give us the amplitude as 4 centimeters. So that is it, 4 centimeters. And now we are asked to find the period. These are just the only two things they gave us. So question I says we should find period. So period is capital letter T. And since I know frequency, I already know that period is simply 1 all over F. You see that? Very simple. So this implies that period T is equals to 1 all over 50. And of course, if we do 1 all over 50, that will give us about 0.02. 1 all over 50. Yes, that is it. 0.02. And the unit, of course, is going to be meters, because frequency is in hertz. So oh my God, second, not meters. 0.02 second. So frequency is in hertz, and then your time, your period also has to be in standard unit, and that is second. Now, but notice that the question they gave to us, amplitude, is given in centimeters. So let me quickly convert that before we use it like that. Amplitude 4 centimeter, converting it to meter is going to be to divide it by 100. And if I divide 4 by 100, I'll be getting 0.04 meters. So anywhere we have amplitude, I'm going to be using 0.04 and not 4 centimeters. All right. So that is how easy that first question is. Now, the next one says we should find the acceleration at the middle and at the end of the path of oscillation. That's the second question. We should find the acceleration at the middle. So back to this, my diagram here. Look at what they want us to do. They want us to find the acceleration at the middle. The acceleration here, and the acceleration here and here. That's what the question is saying. So what is the acceleration here? And what is the acceleration at this end, the end? That's what they mean. Now remember, at the center, x is what? 0. So at the middle, x is equal to 0. So let's go back. Remember the formula. So number 2, let's find acceleration at the middle. Acceleration at the middle. In fact, let's recall that acceleration, that our acceleration A is given by minus omega square x. Don't forget that. So I can say that at the middle, comma, x is equal to 0. At the middle, x is equal to 0. And if I put 0 back here, it simply implies that acceleration at the middle, A, is equal to 0. So it means that at the center, and I explained that before, there is no acceleration there. So acceleration at the middle is just 0. So sorry about that. So acceleration is simply 0. And if you like, you can put the unit meters per second square, which is very, very important. In fact, put the unit, it's very important. So that is that for that. So acceleration at the middle is 0. Now, but at the end, remember at the end that x is equal to A. Don't forget that at the end, which is the position for the maximum displacement, x is going to be equal to what? A. So let's do that. So acceleration at the end, I can say that x is equal to A. Of course, it implies that my acceleration A is going to be what? Minus omega square A. You see that? That's what exactly it is. So, but there is a little issue, of course, but it is no issue actually. We are not given omega, but I can find omega. We were not given omega at all. But I already proved what you can actually find what omega is, and I'll tell you how. This omega can be found is equals to 2 pi over t, which is equals to 2 pi f. I already said that. If you check what I did before, you'll find out that there was a place I wrote 2 pi over t to be the definition of what? Angular velocity or angular speed. So, but in this case, I can choose to use 2 pi over t, and since 1 over t is f, so the formula can also be 2 pi f. So let me use 2 pi f. I don't want to have fraction. So it means that this my formula A, which is my acceleration, is going to be 2 pi f all squared, then my A. And then if I open up the bracket, 2 square is 4. So 4 pi square. Then of course my frequency is f square, then multiply by a. So everything here is going to be the acceleration. So since I know the frequency, it was given from the equation that the frequency is 50 hertz. And then I know the amplitude to be 0.04. So I'll simply put in every parameter and then multiply. So this will give me 4 times, let me leave my pi like that. If you like, you can evaluate yours, but I want to leave mine like that. So my answer is going to be in terms of pi. So 4 times pi square times frequency is 50, so 50 square, then multiply by a, and a is 0.04. So if I multiply everything here, I'll be having, wait, 50 square, that's, so everything here is going to be equal to 400 pi square. Of course, the unit is going to be in meters per second square. So this negative sign, remember I told you the negative sign, you might feel that I ignored it. So you can put it there, but the negative sign talks about direction. Do you understand that? So it doesn't entail acceleration being negative. So even if I put the negative sign there, what I'm trying to say is that the acceleration is actually on the opposite direction, is acting towards the mean position, opposite direction, as the displacement increases on the other direction. So this is the value, the magnitude of that acceleration is 400 pi square meters per second square. All right. Now we've answered question 2, meaning that we found acceleration. Oh, I answered the third one, which is triple I. We are still doing the same thing. So we are actually answered this. Remember the question, this one we answered there is the third one. We omitted answering the second one, which is the velocity. So we are going to go back and answer the velocity right now. So let's find the velocity at the middle and at the end. Now, the velocity at the middle, recall, so let me call this triple I. Please, you can change the numbering from, if you've written down the equation, you can just change the numbering or just understand. Of course, I know you can follow with what I'm doing right here. All right, so the velocity, recall the formula that the velocity of an object undergoing simple harmonic motion is given as v equals omega square root of a square minus x square. Everything here is in the square root. Do you understand that? But at the middle, they say we should find the velocity at the middle and at the end. So at the middle, our x is equal to what? 0. So the displacement from the mean position is 0 because it's assumed that x has not even moved at all. Meanwhile, the object is moving, but there is no change in position from where it was and where it is. All right. So if x is 0, it means that this formula v is going to be equal to omega a. And I showed you that when I was proving this, and it's very, very important. So I'm going to be multiplying omega a to get the v at the middle. Do you understand that? So v at the middle is given as omega a. So where a is 0.04, and of course, your omega is 2 pi f. So this is 2 pi multiplied by frequency times the amplitude a. So this is 2 pi times frequency, which is 50, then times 0.04. And 2 times 50, that will give us 100. And of course, if I multiply 100 by 0.04, it's as good as dividing it. And that would give me Oh, 100, that's 4. So that is 4 pi meters per second. So this is the velocity at the middle. So the velocity at the middle is simply given as 4 pi meters per second. All right. And also at the end, remember at the end, that our x is going to be equal to the amplitude. So the position from the mean position is actually equal to the amplitude. And if I put the formula here, it means that this form, if I put x as a back to this equation, I have that v equals omega square roots of a square minus a square, and a square minus a square is going to be 0. 0 times omega is 0. So the v at the end is actually 0 meters per second. That is exactly what that implies. So you see, the answer is very simple. The questions are always very simple, nothing difficult. Once you can record the formula, you can always solve the problem. It's not more difficult than what we are doing right here. All right. Now, the third one says we should find, okay, the fourth one now. So we should find the velocity and acceleration at a distance of 2 cm from the center of oscillation. So we want to find the velocity and acceleration at a distance of 2 cm. So at 2 cm, remember, let's find the velocity first. That v is still equals to omega square root of what? A square minus x squared. Don't forget that. So at x equals 2 cm, and of course 2 cm is simply 0.02 meters. So I'm going to be putting, anywhere I see x, I put in 0.02, and then our a is already found as 0.04. So it means that a was given, so v is going to be equal to, our omega is 2 pi f, 2 pi times frequency, which is 50, multiplying the square root of 0.04 square minus 0.02 square. So everything in one square root. So this is going to be 2 times 2 pi, this is 100 pi. Then, of course, if you check let me press it once in calculator. So what is square root of 0.04 square minus 0.02 square? If I press that once in the calculator, that will give me 0.035. So this is 100 pi multiplying 0.035. And if you multiply 0.025 by 100, that will give us, okay, our answer is looking, I don't want it in decimal. I'm going to write the answer in sodic form, and this will give me 2 pi, in fact, 2 square root pi, or better, so 2 square root 3, 2 pi square root 3. I think that's, putting it down this way is better. Please don't get confused by the square root. You can use your calculator, just multiply 2 pi times 0.035. Anything it gives you, 100 pi times 0.035, anything it gives you is the answer. And that thing it gives you is going to be equal to 2 pi root 3. So don't mind the nature of my answer. Use your calculator and you get the same result. Do you understand that? So this is my velocity when the distance is just 2 cm from the mean position. That's, if you trace the position of the object, the displacement from that point is 2 cm from the mean position. This becomes the speed. Do you understand? All right. And also they ask us to find the acceleration at 2 cm. So it means that at 2 cm, for acceleration, the formula is simply a equals minus omega square x. And this x is the acceleration from the mean position. So I'm going to use this to be 2 cm. So the x is 2 cm, which is 0.02 meters. So this will give me minus 2 pi f all squared, then multiply by the x. And of course, our x is 0 times 0.02. And this is 2 pi. So 2 square is going to give me a 4. And this 4 pi square. Frequency is 50. And this 50 square times 0.02. And if I press everything out here in calculator, keeping my pi square constant, I'll be having 4 times 50 square times 0.02. That would give me 200 pi square. Of course, the unit is meters per second square. So this is going to be the acceleration at a distance 2 cm from the mean position. And that is exactly what I have right here. And now, the next thing says we should find the angular acceleration at the end of the path of oscillation. So let's do that. I want to believe everyone is following. Please, at any point you don't understand what I did, or something is confusing for you, just help me by calling my attention so I can explain that real quick. Even though you can always go back and make reference to the videos, and I believe when you do, you will always understand every details. All right, the last one says we should find the angular acceleration at the end of the path of oscillation. So how do we find the angular acceleration? The angular acceleration, this question V now, angular acceleration is given as alpha, and alpha is equal to simply, I prove that as A all over R. And since A all over X, I use X position. So alpha is A all over X. And if alpha is A all over X, and then, of course, you know they said at the end. So at the end, it means that our X is equal to what? Our A. So it means that alpha can be given as A all over capital letter A. And then alpha, I already found my A to be, I already found my A to be 200 pi square. So this is going to be 200 pi square divided by A, and our A is what? 0.04. And anything you get from this result becomes mine. So let me quickly press that from my own calculator. So if I have 200, I'll still keep my pi square constant. So I want my answers to be in terms of pi, but you can choose to evaluate yours if you care. So 200 divided by 0.04, that's going to give me 5,000. All right, so this is going to be 5,000 pi square. Now the unit for angular acceleration is radian per second. So radian per second square. Radian per second square. And that is the angular acceleration of this body undergoing SHM. And that brings us to the end of that question. Okay, now there is another form or another thing you need to know about in this simple harmonic motion, and that is the period of simple pendulum in simple harmonic motion. So many a times they can give you a pendulum experiment and you'll be asked to find the period. You'll be asked to find what is the period of this object, and the setup they gave to you is that of a simple pendulum. So take note of that. Simple, the period of simple pendulum in simple harmonic motion. The period of simple pendulum in SHM. So that's the heading. The period of simple pendulum undergoing SHM. That is it. Now, in as much as I would want, in fact, let's not prove the equation. So I'll just give you what the formula is, and then at any point you see it, you can easily identify and use it to solve problems. So the period of a simple pendulum undergoing simple harmonic motion can be given as that T is equal to 2 pi multiplied by the square root of L all over G. So this is the period of a body undergoing simple harmonic motion. So anytime you have a body, a simple pendulum, a simple pendulum experiment, the period of that body is simple pendulum, provided a simple pendulum is in simple harmonic motion, the T there is given as 2 pi root L all over G. Now the question is, what is L? What is G? Because 2 pi is a constant. So where L is the length of the string, so I need to be mentioned, or you'll be asked to find it. So where L equals the length of the string, and the string is just the rope. So when you hear string, we're talking about just rope. So, and then it has to be inelastic, and then the G is a constant, which is called your acceleration due to gravity. So that is it. And oftentimes the acceleration due to gravity can be given, and sometimes it won't be given. But whether given or not given, the value is always 10 meters per second square. That is the best value to use. Sometimes it can be given as 9.8, 9.81, 9.83, whichever. But if you're not given, just use 10 meters per second square and do your solution. But if you are given, stick to what you are being given and do the same thing. And now, remember that period, let me try to change this formula now. Now, recall that period T is equal to, or frequency is 1 all over period, or period is 1 all over f. So recall that period is 1 all over f, or which implies that frequency is equal to 1 all over period. So it means that I can equally write my frequency in terms of this formula I've just given to you by taking the reciprocal or the inverse. So it means that the frequency of a body undergoing simple harmonic motion can also be given. So this implies, therefore, the frequency of a body undergoing simple harmonic motion, the frequency of a body of a simple pendulum undergoing simple harmonic motion, that's the best way to put it, is given as F equals 1 all over 2 pi, then square root of G all over L. And I want to believe you understood what happened here. Just take the inverse. You can go try it out and see whether, take the inverse of the original equation, that of period, you find out that you get exactly what we have right here. So what does this formula even imply, these two formula? So it means that from the first one, I can interpret that formula. Look at it, this one. I can say that the period of a simple pendulum undergoing simple harmonic motion is directly proportional to the length. You can see that the length is up. And then it is inversely proportional to the what? Acceleration due to gravity. It doesn't have any business with the mass. There's no mass whatsoever consideration. So it doesn't mean mass is not, we don't consider mass when we are looking for period. So this period is directly proportional to the length and inversely proportional to the what? The acceleration. But the acceleration due to gravity. But the frequency is directly proportional to the what? Acceleration, and then it is inversely proportional to the what? To the length. Do you understand that? So it is very, very, very important. Meaning, as the length of the body undergoing simple harmonic motion is reducing. Of course, if you've ever been in the laboratory and you did anything with or under simple harmonic motion, you will know that if the length of the string is small, the frequency is going to be higher. So if the body is moving, let's say I'm using a longer string, it will be moving something like this, small, like this. But the moment I use a shorter string, it will be moving like this. So it will just be moving faster. So the shorter the length of the string, the higher the frequency. Do you understand that? And the shorter the length of the string, of course, you're going to know that the shorter the length of the string is, it will become the more, no, the shorter the length of the string, the higher the period, the shorter the period, but the shorter the length of the string, the higher the frequency. That's exactly what I'm trying to say. I don't know what okay, but that's by the way. So take note of that. If the length of the string increases, the frequency is going to reduce, but the period is going to what? Increase. No. If the length of the, yes, I'm correct. So if the length of the string increases, then what will happen is that the frequency is going to decrease. Of course, the period equal is going to increase. So that is that for that. So take note of this formula, as it is very, very important. Then, is there any other thing I'm missing out? Is there any other thing I'm missing out? Okay, we've not looked at energy. Okay, but there is another formula too. And now that is the period of a mass suspended on a spring under simple harmonic motion. The formula looks like this, but just a slight difference. And that is that of simple harmonic oscillator. Is also similar to what we just have here. So you can put down a heading like this: the period of a mass suspended on a spring in simple harmonic motion. The period of a mass suspended suspended on a spring in simple harmonic motion in SHM. So how do we find the period of a body that is being suspended at a string undergoing simple harmonic motion? And it's also likely just similar to what we did just now. So for such kind of mass suspended against a spiral spring, of course, with negligible mass, we can find the period using this equation that T is equal to 2 pi root m all over k. The other one is 2 pi root L all over G. This one is 2 pi root M all over G, root M all over K. And get the difference. Get the difference that this, for this formula, we are talking about a mass suspended on a spring. On a spring, where M is not the mass of the spring. So we always consider the mass of the spring to be what? In fact, the spring, we assume it to be massless. So we assume the spring doesn't even have mass. So we say it has a negligible mass. So the mass is almost zero, or is taken to be zero. All right. So this mass here is the mass of that body undergoing simple harmonic motion. Do you understand that? So M is the mass of the body undergoing SHM, and then K is simply the force constant of the spring. So every spring has a force constant, and I'm sure you can remember your Ohm's law. So K is the force constant of the spring. The force constant of the spring, and that is that for that. Okay, so one more thing, our time is almost up. One more thing before we bring the class to a close, and that would be the energy of simple harmonic motion. The energy of simple harmonic motion. I'm trying to see that I touch everything, every area under this topic. So when you read, you can easily understand. So the energy of SHM. So how do we find the energy of a body undergoing simple harmonic motion? Now, especially if you have that of, remember, at any instant in time, the system contains the same energy. So it means that the kinetic energy, the total energy of the system is going to be the sum of the kinetic and potential energy. That gives us the, in fact, for a body undergoing simple harmonic motion, put it this way, for a body undergoing simple harmonic motion, the total energy, let me call it E subscript T, is going to be equal to the sum of the kinetic energy plus the potential energy. So this is what it is. The sum of the kinetic energy and then the potential energy. And for a spiral spring with mass M suspended on a spring undergoing simple harmonic motion, the total energy can be given as. So anytime you have anything that has to do with mass, anytime you are solving it, you're giving a equation under simple harmonic motion, and then they are telling you that the mass is being hung on a string, and they want you to find the energy or the total energy of that body. So we can find the total energy to be that W is equal to 1 all over 2 Ka square. So this is actually the total energy of a body undergoing simple harmonic motion for any body on a string. For any object that is hung on a spring undergoing simple harmonic motion, the energy can be calculated as this. Remember that K is simply your what? Your force constant. And of course, your A is nothing but the amplitude of that body. So if I want to rewrite this equation, I can write it this way, that my W, which is the total energy, is going to be the sum of the kinetic energy plus the potential energy. And if I plug in what their parameters are, it means that the W, which is 1 all over 2 Ka square, is equal to kinetic energy, which is 1 all over 2 mv square, then plus potential energy. And what is potential energy of a body on a spring? It is actually 1 all over 2 kx squared, where x is a displacement of that body from the mean position. And this is what the equation is. So take note of this. Basically, this is what I want you to take measure on this. So anytime you're being asked to calculate the energy of a body undergoing simple harmonic motion, for any mass hung on a spring, most of the times that is how the questions will come. So you'll be using this formula 1 over 2 Ka squared. And this is exactly what it is. But if you are asked to find the total energy on the system, then it means you're going to be adding up the kinetic energy, which is 1 over 2 mv squared, plus 1 over 2 ks squared, which is the potential energy. And the sum of these is going to be equal to what we have here. Anything you calculate as this thing here is going to be what? Equal to what we have here. And what does that imply? That implies that energy is being conserved. Of course, if energy is conserved, the energy before is going to be equal to the energy after. So that is what this whole thing entails. And at this point, I will want to bring the class to a close. And if you have a question, you may just ask. Later on, I'll just send in an assignment you will do, and the assignment will help you to practice this. You remember I didn't give you any formula on this very topic. I didn't give, sorry, on this very heading. I didn't give any example. So I'll be sending an assignment. Just the formula is very simple. You put in the values, look, read the question, understand the question, and use the formula, and then solve the problem. That is how it is. It's not difficult at all. The period is given, the frequency is given, and the rest of that. Just know how to do and make solid formula to find whatsoever thing you're asked to do. And that is all for that. So any question before we bring the class to a close? I have Lucas, I've not taken my attendance, and I think I have to do that right now. And then the names I'm having here, please, if you're active, just mention your name for me. Let me know the names of persons I'm going to take.
Suleiman.
Suleiman. Okay, Suleiman, you're the first person. So just hold on. If you don't mention your name, it means you're not active, and that might mean that your name wouldn't be marked on the attendance. Suleiman. Suleiman. Suleiman, what's your surname?
Abdul Samad.
Okay. Why am I not seeing the name here? I'm not seeing that name on my list.
I used to
Suleiman.
attend, sir.
I didn't see the name on my list here. I'm only seeing, I see Sharon, I see Joshua, I see Sharon, Joshua, Hillary, Osazuwa, Jessica, Dubem. Then I have Success, I have Praise, I have Odalo Godin, I have Ayuba David, I have Muhammad Mudashiru or something. I have Obaomi, I have Ayuba David, I have Gospel, I have Isiri, Osapolo, I have Osazi, Success, Precious, and just like that, and Ife. So the name you called is not on the attendance list. But these persons that I called their name now, please, if you're here, just indicate so I can mark your name. So please, if you hear your name, just tell me what the name is. So let me quickly mark it.
Yeah, man, it's Osaze.
Your name is what?
Osaz Onegu.
Okay. And I will. Okay, that's present. Who else is present, please? Who else is in the class? Let me take the attendance. You see, every other person, they are in limbo. They've left the class and they went to attend to something different. Usually, I take my attendance at the end of the lessons, and I can choose to take it anytime. So there's no even time I can take. I can take the attendance anytime. So who else is in class? Let me mark the attendance before we end the session. All these people that I'm seeing, are they not in class?
I am in class, sir, but my name is not on the list.
What's your name?
Amawagbo Nsiri.
Your name is what?
Omoragbo Esewi.
Siri.
Esewi.
Okay, Siri.
Yeah.
Siri. Okay. Okay, let me check that. Okay, you're right. The name is not here. You and the other young man. But who else? These people here. Does it mean your name is not on the list also? What's your name?
My name
Huh?
is Egwagi Loki.
Lucky. There's no Lucky on my list.
But my
Can't
name is
find
not
Lucky.
in the list.
Huh?
My name is not in the list.
Okay, your name is not on the list. Okay, maybe later they'll have to compile and update that. So who else, for those of you that have your name on the list? This Obaomi, I thought you are you not the one there? Okay, guys, see you all in the next class. Do have a wonderful time.